Okay, hello everyone and welcome back to your YouTube channel and welcome to this very important video today. Today I am creating a video specifically to present how to calculate and define and calculate pre-contingency conditions in a test system. If you remember and if you are following the video series, in my previous video, I create a test system inside the DIgSILENT Power Factory. Specifically, it was a single synchronous machine connected through a transmission system to a infinity bus bar, okay? At that moment, we spent time making calculations of the reactance in real units, ohms, in order to be set up inside the DIgSILENT Power Factory, okay? I remember that we conclude that video running a basic load flow, but not so much considerations about the real condition that we can find in an electrical power system. Today, I am dedicating this video to explain how to define and how to calculate pre-contingency conditions in a test system, okay? And to start with that, let's do the following. Let's go for business here, and you must remember this test system. This is a three-phase power system. This is 50 Hertz. All of you must remember we are based in Europe at the moment, and as a consequence we are using 50 Hertz here in Europe. And in this case, this is a synchronous generator, a 100 MVA synchronous generator connected to a bus bar that I call LV, short for low voltage. Then we have a step-up transformer, classical step-up transformer, and it's going from 11 kV to 232 kV, okay? I call this bus bar HV, that is the short name for high voltage side, okay? And then we have two identical transmission lines, and they are going to what we call the infinity bus bar, okay? We are assuming that this synchronous generator is connected through the whole transmission system to a very big, very large power system. In this case, this very large power system, we say that is so large that is an ideal infinity bus bar, okay? Well, you must remember this. This was the case in the previous video. To be honest, this is something that you can find in many power system analysis, books. In particular, I have a couple videos related with manual calculations in this system, but the job today is starting from the model that we create in the previous video. What we want to do today is include the realistic initial conditions, okay? And if you remember, there is a statement, and that statement say that the prefall or pre-contingency condition is a steady state condition. That is clear for everyone here, and the main information that we need to care of is the generator. This generator here, G, delivers an active power of P-elect 0.6 per unit at power factor 0.8 to the infinity power bar, okay? What I am telling you here is that this small line here, this small paragraph here, is giving you a very important piece of information, because they are defining where the steady state pre-contingency conditions are known. In this case, it's clear that the generator is delivering an active power of 0.6 per unit here at the infinity bus bar. And the second important thing, and probably the most complex that you need to take care, is that the power factor is defined here at the infinity bus bar. And what is the issue? Okay, the issue is the following. The issue is if you remember, we know data here. We know the electrical power is 0.6. We know that the power factor is 0.8. And using this equation, all my students, they took a previous module about electrical power system, and also they have a bachelor in power engineering. They must be able to calculate the reactive power. And the reactive power here must be 0.45. Okay? What I'm telling you is this very important line over here is defining the power in this side of the electrical power system. And what is the bad news? The bad news is that, okay, we are receiving here P and Q, but the controller that we have in this network, the control that we have in order to deliver active and reactive power, those controllers, they are defined here in this side. Those controllers are located at the synchronous generator. For that reason, we need to think carefully about the decisions that we are about to make, okay? Because, for instance, active power, there is no problem. If I set up this generator for 0.6 per unit, remember that this system is a purely reactive power system. As a consequence, all the active power P departing from here will reach the infinity bus bar because they are not resistant. They are not active power losses. There are no megawatts lost in this system. But the situation is extremely different when we are talking about reactive power. Because the reactive power in this system, they are losses. Because as you may remember, this transmission system have reactance, inductive reactance. This transformer here, there is a reactance, series reactance for the model. And here, this generator, of course, there are some reactance in the stator creating the model. What I'm telling you is when the current is moving through all those components, they are reactive power losses, okay? And we need to take care about that. Because if we are receiving here 0.45 per unit, there are losses here, there are losses here, there are losses here, and as consequence, we don't know by simple way the reactive power that we need to send here. And that is an issue. That is an issue because we need to be sure that 0.45 per unit is reaching this infinity bus bar in order to we start the calculations in a proper way, okay? If you disregard this important line, you will be in troubles because basically what you are doing is ignoring the pre-fall conditions, the pre-contingency conditions, okay? And this is not the first time, okay? I saw this in very important consultancies around the world that people, because they cannot do the full pre-contingency conditions, they start to run calculations with the system that they have. And that is totally wrong, okay? That is totally wrong. You must, the very important point is defining the initial condition of your system, the state pre-contingency conditions in a proper way. If you put over there whatever you want, of course the result will be anything, and it's not related with the conditions that you have, okay? For that reason, I am spending time in this video teaching you how to set up the pre-fall calculations, okay? Okay, I understand that this system is extremely simple. I know some consultancy guys, they say, no, this is a Mickey Mouse power system, because this is something extremely simple. Yes, I totally agree. This is extremely simple, but this is to show you how important it is to define the pre-fall conditions. And it's your job to understand power system analysis. It's your job, know the power system analysis software in order that you can define properly the pre-fall conditions, the pre-contingency conditions, okay? Okay, the first step that I will do is I will show you the first mistake, okay? What's happening if you don't care? What's happening if you don't care about these small lines here that say the power factor is 0.8 here at the infinity bus bar, okay? What I will do is I will do a very simple simulation, a steady-state simulation inside the DIgSILENT Power Factory, and as you will see the difference if you don't care about this very important step, okay? Let's go to Power Factory and I will see you there, okay? Okay, welcome to Power Factory. Now we are here. You must remember we create this model couple videos ago. I explained to you how to create everything. What I have done here is basically just small changes, just very simple changes in order that the system look better, okay? I don't like when I receive a power system and it's a mess, okay? You must be serious. You must create your proper power system, okay? If you are presenting a clean, a very well organized power system, that means a lot about you, okay? It's mean a lot about the quality of your skills, the quality about your interest about what you are doing, okay? It's very important that you present properly your power system, your test system, your results, your report, okay? Because that means that you are doing the things with passion and you are doing the best of your job. I don't like when I receive a power system that was creating a rush and it's a disaster, okay? Okay, but it's time to discuss the subject that we are carrying off in this video. This is time to talk about the pre-contingency analysis, okay? If you remember, I say to you that we need to define the steady-state pre-fall condition or pre-contingency, okay? And I remember that I say to you that the statement, if you go back to the presentation, you must remember that we say that the active power here should be 0.6 per unit, but the power factor that is shown here should be 0.8, okay? If you calculate the reactive power, that means that the reactive power here should be 0.45, okay? Inside Power Factory, we are not using per unit directly, but we are using real values, okay? And in this test system, as the base power is 100 MVA, well, here I will see 60 megawatts. That is 0.6 per unit, and the power factor here should be 0.8, okay? What is the classical mistake? The classical mistake is that my students or some people, they are in a rush or they don't care about the initial conditions, and they go here to the synchronous machine, because here inside the synchronous machine is the place where you have the controllers, okay? If you go here to the tab of load flow, well, of course, you can select here different local controllers, okay? You can select constant V, or you can select voltage Q drop, or you can select constant Q. I mean, there are several controllers included inside the DIgSILENT Power Factory. If you want to know more, please go to the technical reference of the synchronous machine inside the DIgSILENT Power Factory, okay? Power Factory has made a lot of effort creating a very beautiful documentation, okay? But coming back to my explanation here, a classical mistake is that the student or anyone read, I need to deliver 60 megawatts, and they define here constant Q, and then they go here and they say, okay, 60 megawatts, done. And then they say, but the power factor should be 0.8. And they include over there, they use the input 0.8, okay? And now let's run the power flow. If we run the power flow here, what is happening here, okay? as you can see, this machine is producing 60 megawatts, 60 megawatts, and 45 MVR. Okay. What I will do here, because Power Factory is not showing you the power factor directly, what I will do here is just show you that. Let me unlock here, yes, and let me do the following. Okay, I will add here to this device. I will add text bots. I would like to create an additional result bots. Okay, that is what I will do. Okay, right button, then you go to text boxes, and then create additional result bots. Okay, and right now Power Factory is creating here an additional result bots. Okay, what I will do is edit the format, and now you can see over here there is a window, a very interesting window that allow you to configure to define the settings for what you want to represent, what you want to show in the additional result bots. Okay, I prefer this approach. Because I don't want to destroy my general presentation, my general results inside Power Factory. Okay, I know that they are many of my friends that they are top users of Power Factory. They will tell me, no, there are other ways to do this. To be honest, I am doing this in a very simple way, just to show my students how to do it. Okay. What I did is right button here and append an arrow. That is just to say Power Factory, I want to add an arrow, and now I can define the kind of results that I want. Okay, in this case, I will go here. You can see this is this window is to show you the internal monitoring variables, and in this case we select here lot flow, and what I want to show is here. Okay, you can see that there is here we have active power, we have reactive power, we have apparent power. Let me show also apparent power. Okay, and now we have here as you can see, we are showing the power factor, we are showing the apparent power. Okay, another cosmetic thing that I will do is, because some of my students, they want to see, you know, which variable they are looking, and also they want to see the units. This is a very basic option. I know a few of my friends that must be laughing at this moment, but what I have done is to include here the variables. You can see the variables, but also if you select here adapt width, now you have here a full result box over there. Okay, and what is the interesting thing here? Okay, my dear student, if you look those results, okay, you are producing 60 megawatts. Okay, and that 60 megawatts is coming from this generator and arriving here. Perfect, it's no a problem. The problem is the reactive power, because if you look over here, this machine is producing 45 MVR. That is the reactive power produced here at this generator, and you can see the power factor is 0.8. But if you look here, the reactive power Q is 32.2 MVR. Okay, what I will do now is I will include here another result, additional result bots, in order that my students can see that the power factor at this very specific infinity boost bar is not 0.8. Okay, what I will do here is let me go where are result boxes. Okay, then create an additional one. Jesus, I didn't do it in a proper way. Right now, yes, right button, text boxes, create additional results. We have here additional results. Okay, but now we need to configure this. What I will do is here is edit the format. Okay, and what I will do again is adding append an arrow, and then I will select here, as I did before, Let's add the power factor. The power factor is here, and also S, apparent power, okay? And if you remember, I select here, and I showing to my students the units, okay? And everything that they want, the variables, names, and the units, okay? Adapt with, voila, we have a problem here. What is the problem? That the original statement of this very specific problem say that the power factor here should be 0.8. And somebody make a mistake, he went in a rush, I don't know what happened, but this person put here 0.8 power factor at this very specific location. And that is a no-no, okay? This is a no-no because as you can see over here, the power factor at the infinity boost bar is 0.88, and that is different to the value that we need to have. Probably some people without a strong background in electrical power system will say, no, but 0.88 is similar to 0.8. That is totally wrong, okay? When you are working with power factors, remember that that is the cosine of the angle. And when you are working with low power factors, you are going into the nonlinear region of the cosine. For that reason, small changes, small values look small, but that is not true, okay? It must be 0.80, okay? Anyone making this mistake, this is a terrible mistake. And also, if this value is not 0.8, the important thing is that you are changing the initial conditions of all the state variables in your power system. And when you do so, you are solving another condition. And as a consequence, if you are analyzing power system stability, you will say that the system is stable, but the condition that you are analyzing is not the one that you need to be doing, okay? That is a no-no. That is a massive mistake. You must be ensured that the pre-fall condition, the pre-contingency condition is properly done, okay? Now, what we need to do here, my dear students, what we need to do here is basically solve this problem. And how do we solve this problem? Well, my dear students, the issue is we have the controller is on the left-hand side at the generator. And we need to have the control of the reactive power. I mean, the controller should be here, but the variable, the interest variable, is on the right-hand side. And that is where we need to do something quite clever, okay?